Hello everyone. In this module, we're going to look at the source folder inside the QNE application. In the previous module, you saw how the configuration files are created when you type in the QNE application create command. In this submodule, we're going to look at how we can actually populate the source folder with the application logic that we want. So let's just go ahead and start with our boilerplate code. For that, we type in QNE application create name of the application, which is my app, and the two roles that I'm going to assign for this application, which is Alice and Bob. So as you can see, this will create a new application, my app, inside the create folder. Inside the source folder, you'll see Python files for the two roles that we have defined, Alice and Bob. Now in this submodule, we'll see how we can populate these files with the application logic. Suppose, let's take a very simple application, which is to create entanglement, measure it, and return the result. In order to do that, we use a Python SDK called NetQASM. Now in the same way classical computers have assembly language in them, quantum network applications are also run on quantum network application assembly languages, or NetQASM for short. However, in the similar way, classical assembly languages are very long and very complex for humans to understand, quantum network assembly language, or NetQASM, is also very hard and complex for humans to understand. That's why we have a Python SDK that will help us in writing high-level code in Python, which will then be compiled into the assembly language, which will then be run on a quantum hardware. Let's take a look at NetQASM and see how we can use it in our code here. Now to start off with, for every quantum network application, there are three main items that you might come across very frequently. One of them is a classical socket, which is used to send classical message between nodes. The other one is an EPR socket, which is used to generating EPR pair. The final one is a NetQASM connection object, which is used to connect to the quantum hardware in the backend. So for our application, since we are creating entanglement and measuring it, let's go ahead and create the two objects that are necessary, which are the EPR socket and the NetQASM connection code. Let's go ahead and import them. We import our EPR socket using the following command: from netqasm.sdk import EPR socket. Similarly, we import our NetQASM connection using netqasm.sdk.external import NetQASM connection. Since Bob is going to need the same things, I'm just going to copy it and paste it. Now the application logic required for this protocol will be written inside the main function. Let's go ahead and do it. Since we want to create an EPR pair, we're going to create the corresponding socket for it. To that, we write the following command: EPR socket equals EPR socket, and we're going to pass in the name of the node that we want to have the socket connected to. For Alice's case, it's Bob. So we're going to pass in Bob. Next, we're going to create the NetQASM connection object, which will connect to the backend hardware. For that, we type in the following code: Alice equals NetQASM connection, and we provide in the two arguments required for this object, which are app name, which is provided by appconfig.appname, and the EPR sockets. And we're going to pass the EPR socket we have created before in the list. Now since Bob has to do the same initialization, I'm just going to copy the code again and paste it here. But of course, changing the name. Bob needs an EPR socket with Alice, and Bob is creating a NetQASM connection object. Now that we have the elements required to run our protocol, let's go ahead and start it. The application logic for every application will be written inside a Python context. Let's go ahead and write the one for Alice. We start off by applying the with statement. And now we create an EPR pair. In this application, I've chosen Alice to create the EPR pair and Bob to receive it. EPR equals EPR socket dot create keep. Now this will actually return a list. We are interested in just the qubit, so we extract it by typing in 0 syntax. Alice is now going to measure it and save it into a variable called m. M equals EPR dot measure. Now it is important to convert this measurement result into an integer because that is what we are after. So we're going to cast it by using the following command. Int equal. And finally, Alice returns this result. This is provided as follows. In a dictionary, we type in from Alice, we get m. Now we get to write Bob's application logic. Similar to Alice, we have to create a context with Bob. And the way in which Alice created an EPR pair, Bob has to receive it. So we type in the following command. EPR socket dot receive keep. And similarly, we are interested in the first qubit, so we apply the index 0. Now it is important that Bob actually receives this qubit before moving on further. To do that, we apply the flush command. The flush command makes sure that all the commands written before will be executed by the quantum hardware, and then it will proceed. To do that, we type in bob.flush. Now similar to Alice, Bob will measure his pair of EPR. Convert it to an integer and return it as a dictionary. Now this concludes the application logic required for our very small scale and simple quantum network application, which is just creating EPR pairs, measuring it, and returning the results. Now let's go ahead and create the corresponding experiment. To do that, I type in QNE experiment, create the name of the experiment, which is myEXP, the name of the application from which this experiment is created, which is myApp, and the network I want to run this experiment in, which is Europe. If you do that, you'll see that a new folder is created called My Experiment. Now to run this experiment, I type in QNE experiment run and name of the experiment, which is myEXP. As you can see, this experiment is run in the local server. Currently, it is not connected to an actual quantum hardware, and this application that you have written so far will be executed in a simulator called NetSquid. It will also create a new folder called results. If you open up the results, you'll see the process.json file, which actually contains the metadata for the experiment that you have run so far. You see that in the round result, which is just one that we have right now, Alice has gotten result 1 and Bob has also gotten result 1. This is expected because they have created a perfect EPR pair, and whatever result Alice has measured, Bob should also measure the same thing. Now that you have seen how you can build an application in Q&E from the ground up, let's take a look at a fully fledged application. In order to do this, you first have to log into Q&E. You can do it using the command Q&E login. I've already logged in, so I would not have to do this again. Now, to see a list of applications that are already available in the community application library, you have to type in Q&E application list. This will fetch all the applications that are present in the hardware that you have personally, as well as remotely. At the time of the recording, you can see that there are 12 remote applications and also 14 local applications that I've created on my own. Let's go ahead and clone an application that is present in the community library. I'm going to first change my folder to the clone one. And now I'm going to clone the application. To do that, I type in Q&E application clone -- remote. And this is important because we are cloning an application that is remote in the server. Now I'm going to go ahead and clone the state teleportation application. So I'm going to type in the name of the application. And I'm going to name it how I want locally. Here I'm going to type in my teleport. So you can see it has created a folder called my teleport locally and has filled with the configuration file as well as the source file for the teleportation application. If you take a look at the sender and the receiver, you'll see the logic present in both of them. As mentioned before, all the required libraries are imported beforehand, and the application logic starts inside the main function. The 3 components that are important while running a quantum network application are also specified here, which includes classical sockets between the sender and receiver, an EPR socket from the sender to receiver, as well as a NetQASM connection object. Application-specific logic, for example, in the case of teleportation application, that includes the state of the qubit that you want to initialize in, is also presented here. The same can be said about the receiver file. Sockets are created, the classical and the EPR ones, and also we create the NetQASM object. Once the required elements are created, we start with the application logic inside a Python context. The sender creates a qubit, sets the qubit to the state that he wants it to, creates the EPR pair, does the belt state measurement. The receiver similarly receives the EPR pair and receives the correction values from the sender. As you can see, the sender actually sends the correction values through the classical socket generated before, and the receiver has a corresponding receive message. Once the receiver receives their pair of correction, they apply the Pauli correction on it. Now, before I run this program, it is worth mentioning that because we are doing it in a simulator, especially the NetSquid simulator, we get a lot of functionalities that are probably not available in a hardware. This includes looking at the density matrix of the qubit that we are interested in, and also calculating fidelity through the density matrix. Keep in mind, this is only available while you're in a simulation environment, and actually calculating fidelity would require operations like full state tomography. But for the sake of easiness, we will use a NetSquid simulator We will reconstruct the qubit that the sender intended to send using the phi and theta values. We'll change it to a density matrix, and then we'll calculate the fidelity. From the return statement, we see the type of corrections the receiver has applied, as well as the fidelity of the whole operation. Now we would like to run this application in our backend. As mentioned before, we will run this application by creating the experiment as follows. QNE experiment, create. Name of the experiment is my teleport. Name of the application is my teleport. And the network that I'm interested in is Europe. As before, you'll see a new folder called my teleport being created, and we will go ahead and run it by applying the command QNE experiment run my teleport. As you can see, the return value and the logging that we have done before is printed in the terminal. Now when we open the results folder and click on the proceed.json file, you'll also see the similar results presented here. This includes the fidelity, the original state that the sender intended to send, as well as the received state that the receiver got. Raw output, if you are running this experiment more than once, the raw output for every iteration is also presented here, and you can take a look at it. As a summary, we have seen how a NetQASM application is created for the purpose of QNE. We have seen how there are three main important items while designing a quantum network application, which are creating an EPR socket, creating a classical socket, as well as creating a NetQASM object. Using these, we create our application code inside a context written in Python. This is then transferred to a NetSquid simulator, which will simulate the application for us. In the next submodule, you're going to see how you can upload these applications to the community application library so that people around the world can see what you have written. Thank you.